Okay, I make that time. Thank you very much for coming along. It's great to see quite so many people in for a session in an afternoon that's a deep dive into kind of high-performance code. So obviously no one's asleep yet, and they've still got some capacity to take this stuff on. Welcome, my name's Steve. I'm a Microsoft MVP and Pluralsight author. My day job is as a senior developer for a company called Magix, based down in Brighton, where we do software as a service recruitment technology mainly. I also run a meetup group down there called .NET Southeast, which is a monthly event. So if you're ever in the Brighton area, check us out, and hopefully you can come along and join us. Today we're going to talk about writing high-performance C# code, and I do want to highlight this bit.ly link here. So bit.ly/highperf.net is where you'll find all of the slides and all of the code that I'm going to show you. So don't feel that you have to photograph every slide as we go through. If you go there, you've got it all. So make sure you've got a picture of that, and you can follow along later. If you want to get in touch after the talk, I'm online at Steve J. Gordon on Twitter, and my blog, stevejgordon.co.uk, has a lot of the content that I'm going to cover today in a much more detail. So in some form or another, you'll be able to kind of dig into some of the stuff. If it doesn't make sense today, hopefully those blog posts will sort of take you through the rest of it. I'm going to try and pack in a lot in 60 minutes. So in the interest of optimizing this piece of the talk, we'll skip past it. So I want to start by talking about the aspects of performance, because I think it's really important before we start talking about how we optimize the code, we understand what we're trying to achieve. So for me, I boil this down to three kind of main areas. And the first is kind of raw execution time. And this could be the execution time of perhaps an entire process within your application code. But quite often, this could be sort of measuring how long does a particular method or even parts of the code within a method take to actually execute. Because as a general rule, the faster we can make our code execute, the more we can do with that particular device. Pretty closely tied to that is throughput. And this is a measure that's actually more easy to measure in production, because this is something you can track over time. And it's quite well affected by execution time. And this is a measure of sort of kind of how much work you can do. So in a web application, this might be requests per second, for example. In a queue processing service, a worker service, you might be measuring how much you can actually process of that queue in perhaps a minute or an hour. And this measure, as I say, you want to track in production because you can kind of see trends over time. You could alert on this data if some of those numbers go down. You're handling less requests than you were expecting you could per second. That might be a sign that something that's been recently deployed has affected your code. And again, tied quite closely to both of these is memory allocations. And if you've watched people like Ben Adams on Twitter or David Fowler from the Microsoft team, you'll see them quite often talking about trying to sort of allocate less in their code. The reason this is important is although allocating is a very fast and quick operation, creating a new object is not really problematic, we do pay for that at some point later in time. So anything we allocate on the heap is going to need to be garbage collected at some point in time. And that introduces potentially short pauses in our application while that takes effect. And this can have an impact in high-performance situations on how your code is overall going to perform. If you're giving CPU time over to the garbage collector, that's time you could be spending in your own code. So these are sort of the key areas that we're going to look at and see how we can potentially optimize some of these areas in the code today. It's important to remember that performance is contextual. A lot of what I'm going to show you today is not relevant to your day-to-day pieces of work. You're not going to want to go and apply these techniques in everything you do. But there's going to be maybe 10% of the time where you are writing something where it needs to scale or handle huge volumes, where looking at more performant code could save you time, money on how you're going to scale that service. So bear in mind that this is all contextual, and you need to think about, in your given situation, is it appropriate to go to some of the depths of what I'm going to show you today. It's also important to remember that with performance, there tends to be a bit of a trade-off with readability of your code. And so you've got to kind of think, is it more important that the code is easy to maintain? And if it's regularly changing, you've got lots of developers working on it, you probably want your code to be reasonably readable so that you can maintain it and make changes. But if the code is a microservice and it's designed to do one thing and you're writing it once and hopefully not modifying it too often, then that's the time where you might be able to say, well, actually, if we introduce some of this high-performance code that we accept is going to make it harder to read, we're not expecting to change that too often, and actually the benefit of scaling that service less or being able to do more with one instance is actually worth the time and effort to do it. So just be aware that there are some trade-offs to these things. So when we start looking at how we're going to improve our code, we're going to go through what I've sort of deemed the optimization cycle. It's a pretty simple cycle. We start by measuring. It's really important in performance optimization not to make any kind of assumptions about what you're doing. Even things that you've done in the past that have improved code somewhere may not actually have the same effect somewhere else. So measuring your code is vital, really, to validating that what you're doing is having a positive impact. The first step is measuring before you do anything. Find out what the current state of the application is. That may be starting with a higher level profiling type approach to understand what are the hot paths in your application. And then once you know where the code is being executed often and what's being called the most, then you can start to focus in on doing sort of code level benchmarking and actually looking at optimizing those pieces of code and improving them. Once you've got those measurements and you know your starting place, then you want to begin with some optimization. And in this phase, it's important not to get carried away and do tons of changes at once. It's quite tempting when you're doing this to go, oh, I can apply a span here and this there. And all of those changes at once mean that you don't really know if all of the changes you're making have had a positive impact. Overall, you might have improved execution time or reduced memory allocations, but is that the best you could have achieved? The best way to tell this is to change one small thing and then measure again. And at that point, you can validate your previous assumption, make sure that you've had a positive impact, and then try the next thing. And really, that's just a simple cycle that you're going to keep going through. And depending on what your objectives are for that application, you may go through this once or twice, or you might keep going at this until you really think you've hammered every ounce of performance out of the code that you're trying to improve. So there's various tools available for measuring application performance. I'm not going to go into these in too much depth, but I do want to kind of touch on them just so that you're aware that these are sort of a starting place for a lot of your code. So in terms of profiling, Visual Studio has some quite good tooling built in these days. So I think David Fowler was showing this the other day. You know, there's diagnostic tools built into Visual Studio that you can even run while you're just debugging your code. And even there, you could do things like see what your memory traffic looks like, take actual CPU or memory snapshots, and analyze them as your code's running. Now, be aware that you're in debug mode, so your code's not in the most optimized compiled version. It's designed for debugging, so it's going to be slightly off from the performance you'd see in a release application. But it's a good indicator. You can start to have a feel for what bits of your code do allocate and what sort of volumes of memory you're talking about. Once you've sort of done it in debugging, you're going to want to do some profiling, hopefully under sort of very realistic loads. And this might be in some kind of replica environment where you can hit something with a number of requests that mimic what you've seen in your real production system. Or in some situations, you might be safe enough to take some form of profiling in your production app. And you might use Visual Studio tools to do that. Purview was shown again by David Fowler, quite a low-level tool, quite hard tool to actually get your head around, but very powerful, lots of options there. JetBrains do .trace and .memory, which are kind of a nice middle ground. They offer a little bit more power in some areas, but they have a better UI, make it a little easier to work with. And occasionally, and this isn't something you're necessarily going to have to do all of the time, you might want to even look at the IL code, the intermediate language that your C# or F# code is compiling into when you build your application. Things that you can sort of see in there, you can sometimes get a hint of where you're doing some boxing operations, or you've got lots of virtual method calls going on, or just the raw number of instructions can give you an indicator that perhaps you can optimize that code somehow. As I say, it's not something you're going to all of the time, but it's there as another sort of tool in your chest that you can kind of go for. It's also important to remember that you do want to be monitoring this stuff in production and having real metrics around it, particularly if you are going to be trying to change a lot around performance. Sometimes in your test environments, you might see positive gains. You want to make sure you're realizing them in production and you're monitoring over time so that you can alert on changes in those environments. So these are sort of important tools to figure out where they fit into your development processes. But the tool I will spend more time on today, because it's more sort of akin to direct code improvements and actual sort of code performance optimizations, is benchmark.net. So this is a library that you can bring in. It's an open source library. It's very well maintained. And what it's about is doing high precision monitoring of your code. And this is giving you really good, accurate benchmark results about memory allocations, execution time of code. Typically, you could get really basic results by putting a stopwatch around some code, but you would have to run that actually quite a lot of times to get a very realistic count, particularly on pieces of code that are only executing over nanoseconds, because getting an accurate measurement of that is very difficult. So benchmark.net does this very scientifically. It will do many tens of thousands of iterations of its benchmarking so that it can cast out the outliers, give you a statistical average on the data that it's collecting. And it will also measure its own overhead, so it's ensuring that the actual measurement process itself isn't affecting the results you're seeing. So this is a very scientific way of going to collect the data. And this is the tool that Microsoft now use within CoreFX, which is the .NET Core sort of framework, and inside ASP.NET Core for making sure that they understand how that code base is performing as well. So it's a very powerful tool, and you can also include it in your CI/CD process if you want to. So you use it while you're improving your code, but you could also have these things execute on builds so that you can see if you're actually introducing regressions around any areas of your code that you've kind of identified as critical paths that you don't want to break. So we're going to have a look. This is like the hello world of benchmarking. So we'll start with this. So basically what you'll do is you'll create a console application and you'll bring in the benchmark.NET libraries. So a bit like creating unit test projects. And then we're just going to have a very simple program main method here, which is going to call down to the benchmark runner. So there's various ways you can have benchmarks execute. The simplest way here is just to say to run and then give it the class that contains your benchmarks that you care about. And so below I've got my benchmark class here. So at the moment, I've got this attribute at the top, which is a memory diagnoser. So this is where benchmark gives us control over the type of information that's collected and reported on. Here what I'm saying is I also want, as well as execution time, I want some details about memory allocations when you run benchmarks within this class. Then I have some setup code. This code is outside of my benchmarking. I'm not measuring the heap allocations or the cost of establishing these objects. This is objects that I'm going to operate on. What I'm interested in is testing what it takes to run that getLastName method of my parser type. So inside this method here, which is marked with the benchmark attribute to identify as a benchmark that you want to run, we have some code. And this could be code that points to another project reference that you've got, but it could be just arbitrary lines of code in there that you want to test in isolation as well. So we've got our benchmark. We're going to run it now. So what we're going to do is we're going to make sure that we're on a release build. Benchmark.NET will not let you run the tests on debug code. So it will give you a warning. It's quite obvious if you've done it wrong. And you're just going to run the code inside that console application. So it's going to run for a while. It's going to spit out a lot of information about all of the warm-up phases it's going to do, all of the overhead measurements, and then finally all of the actual iterations of the benchmarks it's running. And finally, when you get your results, you're going to have a bit of a summary. You'll find out what sort of platform you were running this on top of. And then for each benchmark within that class, we would have a row. Here we've got the one row. So we can see 163 nanoseconds to execute that particular method. We don't really know at this stage, is that good, is that bad? It sounds pretty quick, I guess, but we've only at this point really established our own baseline for this code execution. Now, because we included the memory diagnoser attribute, we get this additional memory information. So here we can see first some information about potential garbage collections that will occur. So there's various different generations that your objects can live within the sort of managed memory. And this is essentially giving us a view as to how long those objects lived within the code base while those benchmarks were running. So we can see everything is in Gen 0, so all of the objects that were created were short-lived. So that's a bit of an indicator that there's only the allocations aren't sort of large or they aren't living for a long period of time. And we can see this measurement is actually slightly hard to calculate because it's per 1,000 operations. So it's 0.037 per 1,000 operations, which in this case is around 26,000 times. We'd have to call that method before we might have introduced enough GC pressure that a GC would actually have kicked in. So we can see it's reasonably efficient in terms of we're not putting a lot of load on what we're allocating. And we can validate the actual allocation of bytes here as 160 bytes. Now, it's important to remember these measurements may be scaled differently. That might be kilobytes or megabytes, depending on what you're measuring. All of the results will be at the same unit, but you don't always assume it's bytes, basically. And that is now a point where we'd be able to go and start doing some optimization of our code. So I want to now bring in the features that you're probably all here to sort of hear about and see, and the first of which is span of t. So this was released in the last couple of years, and it's generated a fair bit of buzz, I think. I'm always interested, how many people have heard of span of t already? Most of the hands, good. How many people are using it in a production app? Like 1, 2, 3, 4, 5. I can count them across the room. So yeah, this is pretty indicative and pretty sort of expected. I see this pretty much everywhere I ask the question. And I can understand why, because in a sense, Microsoft have publicized this quite heavily because it is introducing the possibility for them to really optimize CoreFX and ASP.NET Core. So they're very excited about it because it's making the framework and the platform quicker for us to work against. But they have always cautioned in those posts, this is cool, don't use it. And they kind of do that because it can get you into a sort of more gnarly world of code, and they don't want everyone picking this up just because it looks cool. I sort of annoy them a little bit by saying, I do think it can be used more than they are promoting it. I think there are more use cases for things like span of t that I've been prototyping where it hasn't made the code too much more complicated, and I have got a reasonably good benefit out of it. And we'll look at some real-world prototypes that I've been doing in a moment for you to kind of make your own judgments on that. But it was introduced in .NET Core 2.1. It is available also for .NET Framework as an additional library package you can bring in. That's referred to as slow span, which is a bit of a misleading term. It's slightly slower than the span that's in .NET Core, purely because in .NET Core they were able to make runtime changes to support the feature being as highly optimized as possible. So they're both fast, they're both perfectly usable, and you can use these in both places if you need to. What span gives you is a read-write view over some contiguous block of memory, which is a very wordy sort of sentence. So essentially, if you think of something like an array, which is on the heap, that's a contiguous block of memory that's allocated on the heap in one nice block. And we can get a span viewer over that, which doesn't sound hugely useful because we can always look at it as an array anyway. But the interesting thing about span of t is that you can target and view memory that's on the heap, but also on the stack, and also unmanaged memory. And you can work with it through this consistent span of t API. You don't need to worry about where the memory exists, and it will do the right thing for you in terms of memory and type safety to make sure that you're not doing things that would be dangerous or allow you to leak objects outside of the scope that they're meant to be seen in. So you can work on things like arrays and strings on the heap, but as I say, you've got that stack option which you can use, and we will see that in use in one of the demos as well, or unmanaged memory if that's where you're working. There's almost no overhead to using this. It has the same kind of functionality as an array. You can iterate over the array, or over the data in the span, I should say. You can modify it. You can take a particular index and adjust that if you want to. And as I say, it's very simple to kind of do those kind of operations in a very similar way to span, with practically, as an array, with practically no overhead to doing it. The most popular operation that you'll do once you've got a span, and this is where you'll start to see the power of it, is the slice operation. This is where we have a view over some data, and what we're going to do is modify that view. So here we've started out with an array of 9 integers, which is a really strange number to use. It should have been 10. But I have my array. So I can call as_span on that, and that will return me my span representation. Now, span is a very low and light type. It's a value type, and it's guaranteed to only ever live on the stack. So there's no allocation or cost in doing this. And it's essentially inside just a pointer and a length over the memory that it's looking at. There's a little more complex than that, but it's very lightweight. So there's very little cost to doing that. Once we have our span view over this array, then we could slice into it. And all we do with slice is we get a start position and optionally a length that we want to use. And this then gives us back another span. So now we have 2 spans looking at the same block of memory. So the important thing is here, this starts to give us the possibility of parsing through some memory that we actually have a view of already without copying it. We're not copying data, so there's no overhead, there's no real cost to doing this. And you can see here that my second span, my span 2, its index 0 would essentially bear where index 2 is in that first span. So both of those can now operate on that data and modify and view it differently. I sort of give the analogy for this of photography. So I do a little bit of photography. I have a DSLR camera with a sort of telephoto lens. Many people have taken pictures with their camera phones. If you're taking a nice wide-angle picture of a landscape and you see an object down the middle of that landscape that you're interested in, you have a couple of options. You could walk towards it, which might be a mile across a field and over a stile, and eventually you get close, and great, you've taken your picture. There's a fair amount of effort involved in that. Or a fairly consistent operation is just zooming the camera lens or swipe zooming into the view, and then you have a different view over the same scene that you were looking at previously. And this is what slicing is essentially. And because of that, it's a constant time, constant cost operation. So because there's no allocations involved, because there's no memory copying involved, it doesn't matter here if that array is 9 elements or 9 million elements. The cost of slicing into it for any length of slice is exactly the same each time we do it. So now I've sort of shown you that and probably bamboozled your brains with span, because it does take a little while to kind of get your head around. Let's look at a slightly trivialized example before we get to more realistic code in a short while. So imagine we have this requirement given to us by the product owner. We need a method that takes an array. It's going to return 1/4 of its elements starting from the middle. I'm sure everyone's had a requirement like this dumped on them at work. So that's the requirement someone in our business had been given at some stage. And possibly this is how they might have implemented it. They might have just used a skip and a take in a link expression to give the data that was being asked for. And they think, great, we've delivered. Now, sometime later, the product manager comes back and goes, we want to turbocharge this thing. We want to make it really quick. We want to make a fortune. This is going to save us some money. And so now we need to optimize that code. So the first thing I'm going to do is I'm going to set up some benchmarks. So there's some additional code coming, but this is our setup, which is a little more complex than the Hello World example. It doesn't have to be, but there's some good reasons for doing this. So the first thing here is this params attribute on the size property there. So this allows us to configure benchmark.net so that it will run this benchmark actually 3 times, or every benchmark in this class, in fact, 3 times. Each time it runs it, though, it will have a different size value in that property. And the reason we might want to do this is it's very easy to get sort of drawn into testing one particular sort of best case scenario that you expect. And we always expect this array to be maybe 1,000 elements. But often there are edge cases to the data that we get given. And sometimes it can be different. The results of your sort of improvements might differ at higher or smaller sizes here. So we're going to test 3 possibilities. Because I've got that, I need some way to set this benchmark method up. So what I've got is just a regular method that I mark with the global setup attribute. And this gets run once before the benchmarks actually initialize. And it's not, again, doesn't affect the execution time or the allocations we see. What we're really just doing is creating an array of the appropriate size that we're going to operate on. So now we can actually write our benchmark. So this is the code that our original developer had written. All I've done here is added a benchmark attribute, in this case with the baseline equals true, which says this is the starting point of code that I'm coming from. So I want to measure everything else against this. And we can run that benchmark, and we get 3 results this time because of the 3 different param sizes that we put through. So we can see that 154 nanoseconds, 224 bytes allocated in the first run at 100 original size for the array. And as we go up, as we might expect, because we were working on larger and larger arrays, we're seeing higher and higher allocations and a longer time for this code to execute. So this is our starting point. We're now armed with enough information that we can make a change and see if we can improve it. So at this stage, we maybe think, well, actually, I've heard link expressions might have some overhead. Perhaps we'll write this code more manually. So we'll create the new array that we're going to copy some data into, and we'll see if that executes better. So we've had a theory. We've made one essentially fairly small change here that we're going to now measure. So in this results, then we can see, well, actually, great. For this first result of 100 items, we're down to a much quicker execution time. And looks like we've made nearly 50% saving on the bytes allocated. So at this point, if we were only testing at the 100 element size, we'd feel pretty good about the results. Because we've added the additional sizes in, we can see actually with 1,000 elements, the gain in terms of sort of allocated bytes is fairly insignificant now. The difference in each case is actually 96 bytes, which is the cost of the link expression being compiled and executed. But otherwise, the allocation cost is pretty much the same. It's obviously quicker to run, so this is a benefit if we're looking for raw execution time, but perhaps we care about memory as well. So we're finally going to introduce span, and as you can see, we're going to be able to use the slice operation to give us the same set of data. This is a slightly unfair test, potentially, depending on what the caller can accept. So here, the other ones were returning an array. Now we're returning a span of int to them. So we're on the assumption that the caller can work with a span and still use that in an optimal way. If we were just casting it back to an array at some point, we probably would have less of a gain. But let's just see what span gives us on the assumption the caller can work with that and continue on an optimized code path. So when we run our tests again, with the span, we're now under a nanosecond. And we have no allocation. So that's pretty good. We feel pretty good about that. And if we look at 1,000 elements, well, we're still under a nanosecond, and we still allocated nothing. And at 10,000, the same set of results. It's a constant time, constant cost operation. So regardless of the fact that we're getting a bigger and bigger initial array that we're testing against, on my particular machine, the slice operation takes about a nanosecond. On other machines, it will vary slightly, but that's a pretty good set of results. So already you can see in just this trivial example that span can be quite a powerful way if you're parsing data and you just want to get a different view on it, essentially, that you can do that with basically no cost. And we can do this with strings as well. So strings are essentially just a character array under the hood. And so we can call as span on a string literal or a reference to a string. But what we get back is slightly different this time. We get back a read-only span. The reason for that is obviously strings are immutable. And if we were given back a read-write view over the data that that string is occupying, we could do some really nasty stuff to the people that trust that strings are immutable. So we can only ever get back a read-only span, and now we just have that view that we can read over and potentially parse through. So in this scenario, perhaps I find the index of the last space character, and then I would slice to get my surname in this simple example. So we can start to do these kind of operations. In this, there's not much of a gain to doing it, but if you're parsing a large blob of tab-separated files, for example, which we do have an example of, you will see that actually the benefits start to add up quite significantly when you just want portions of that data. Now, there are some important limitations to span of t that it's really important you understand so that you know where and when you can't apply it. So the first of these is it's a stack-only value type, and I sort of hinted at that earlier. So what does that mean? Well, it's defined as what's called a ref struct. This is a new keyword that was introduced in C# 7.2. And what this says is this is a value type that you can never store onto the heap. So today, value types may essentially end up on the heap memory at some point in their lifetime. But because this span could be pointed at stack allocated memory, that would be really dangerous, because then we could have this span existing longer before it's garbage collected on the heap, pointed at memory that is no longer what it was originally looking at. And so because of this, because it's built in to the span of t feature, that we're offered this memory safety, this guarantee that we can only ever use it in the right context with the memory that we're pointing at. Because of that, it can't be boxed. That makes sense. We're not going to be able to put this onto the heap. The big sort of changes that might introduce is that you're quite often tempted to add this as a field in a class or something, but because that's then a part of a class on the heap, we're running into the same issue. The biggest and most significant thing I see people run into is that we can't use this inside async methods, basically. We can't have it as an argument or inside as a local variable inside async methods. And a lot of our code today is asynchronous. So in a moment, I'll show you how you work around that, because that would feel like a showstopper, I think, to many of you. And the final thing is, for a very similar reason, it can't be captured inside Lambda expressions. And the reason for those last two is it may not be immediately obvious, because in code it doesn't look like you're breaking the rules. But when you compile these, you end up with a state machine in the case of async, or you may end up with a class for the Lambda closures that exist. And these mean that we're breaking the earlier rules by then elevating this span thing into a field on one of those classes that get generated. So these are all the limitations we're running against. Fortunately, Microsoft also introduced memory of t, and this is a very similar type to span of t with slightly lower performance gains. So it can live on the heap if it needs to, and this is the critical thing. So it can't now be pointed at stack memory, but it does mean that we've got this guarantee that we can use it in some of the places that we can't use span. So it's defined as a read-only struct, not a ref struct, and that's the key thing. That ref struct keyword use is what guarantees that an item will only ever live on the stack. It's slightly slower if you're slicing. It has a slice operation. It's just slightly slower than what the span slice operation will give you. So depending on what you're looking for, it might be perfectly fine to accept that sort of difference. But if you're going for the ultimate performance, you're always going to want to get back to a span as soon as you can. Fortunately, that's really easy. It exposes a span property. You ask for the span that represents that same area of the memory that you're looking at with the memory of t. And you'll combine these two together. So here we're trying to do something that is making the compiler really sad. We're trying to pass a span into this method that is asynchronous. So the compiler will check this and see this risk. It'll identify that this is not a legal operation. And so at this point, we're not going to have compiling code. We can change the code then to accept instead, in this case, a memory of byte. Now the compiler's happy again. And the way we're going to work with this is we could just slice, as I say, that memory, and it looks very similar to what we were seeing with the span, but we're going for every ounce of performance, so we want to use a span operation to slice it. So the way you work around this is you typically then make a non-asynchronous method at the point of where you're working with the data, because once you have the data in memory, there's no real asynchronous methods that you're going to be calling. And then this method can take a span in. So what you're going to then do is try and pass that span from the async method. Well, here we're also breaking the compiler rule. We're trying to create a local variable that is a span. It won't let us do that inside this async method. So the way we work around that is we make sure we just pass it directly into the method here, and the compiler's happy with this. It can figure it out and do the right thing under the hood for us. And this is typically what you'll see in async code. You'll just drop into the memory of t where you need it, and then drop back to a span when you're actually doing your final optimizations with it. So I've talked for quite a while, half an hour. So we're now going to actually look at some code quickly. So the scenario here was that I was looking at building a prototype to optimize some code we had in production. That piece of code reads from SQS, which is just Amazon's queue service. It takes the message, and we want to store it into S3, which is essentially Amazon's object store, their blob store. In order to do that, we need to give it a file name or an object key, and I want to use some of the properties on that original JSON structure to do that. So today, the code is deserializing, getting the properties to build the key, and then actually storing it in there. So if I drop to Visual Studio, which I'm desperately hoping works this time, good. This is like the original code. And I'm going to show you the original code, then the new code, and then we'll look at the benchmarks. I promise I did it the right way. I benchmarked as I went. But it's just slightly nicer for a reveal if I show you the numbers afterwards. So here I have a method, and it takes in this event context, which in this case just has 5 properties. In our actual scenario, it's got many, many tens of properties. But we're only caring about a few of them. And what this original code, which had been slightly optimized anyway, was doing was it was taking that event context, and it was calculating how many of the elements are we actually going to use to build up the object key. And basically, it's if there's no date, we're going to use 4 elements. If there's a date, we'll use the date in the key as well. So then we get this string array of those elements. So we get a string array with the appropriate size. And what we're going to do is start filling the parts of that array with each of the properties that we care about. And inside this getPart method, what it's doing is saying, if it's empty or it's null, we're going to just put in an unknown part. And that unknown part is just a constant string we're going to use when we haven't actually got the data in the property that we're expecting. If we have got data, we're going to try and remove the spaces. Inside that remove spaces method down here, it's a simple, if there's spaces in the method in the string, do a string replace on them. Fairly reasonable. And then the final check is it a valid as an object key? So there's some rules around having only characters and numbers in the object key. So we've got a regex that's checking that for us. And so that's essentially the code, and we're just going to populate the parts of that array. Optionally, we'll do a toString on the date to format that if we have it. And finally, what really happens at the end is we just use a string join to take all of those elements, join them into one final string. We want it to be lowercase for consistency, so we're going to lower it, and then we have our string. So it looks reasonable. So I'll show you the new one. I'm just going to drag down, just to give you an idea, this is more verbose, to be fair. And that kind of goes to that performance versus readability point. And as you can see at the top here, don't worry about it too much. I have some ugly looking code where I'm defining these things in such a way that I can guarantee that I'm going to reduce a mem copy. I'm just forcing all of the performance I can out of this. You don't have to understand exactly why for the purposes of this demo. So the key thing that I want to talk about is kind of how I'm going to use span for optimization here. So I'm going to basically create a character array that I can use as a temporary building area for the file name that I want to generate. And I'm going to slowly populate that with the elements as I'm going through. So what I'm doing is I'm pre-calculating the length. And the reason I'm doing that in this line here is that down here I'm going to do something a little bit clever, which is if it's only under 256 characters, which in the happy path I usually expect, I'm actually going to use stack alloc to allocate the temporary character array on the stack. And then this typically would mean that you would have to use the unsafe keyword and drop into unsafe code if you wanted to work on the stack at all, because it is quite dangerous. You want to make sure you're not over-allocating on the stack, or you'll end up with a Stack Overflow exception, and then you'll end up on Stack Overflow trying to work out why. But if you're only working with small portions of memory, and here I'm sort of guaranteeing 256 characters I'm fairly happy is OK, I'm saying use stack. But I can also here say, actually, if that's too big, just use a regular heap allocated character array as well. But I can represent them both as a span of T. So this is where that kind of transformation to a single type that deals with either memory location is quite convenient. Then what I can do is I can build parts of the string in a similar way to before. And what I pass in here is the part that I want to start including, my span, which is that output working area, and by reference I pass in the integer which tracks my position, so that I can update my position as I go and slice to the appropriate point in the character array as I'm building it. So I'm basically doing what I did before, but slightly more verbose. So if it's 0 length or it's white space only, then use the unknown part. And you can see here what we're doing is basically just saying copy it into that span, starting at the slice that begins at this output position. At the start of this, it's 0. But what then we'll do is update that position so we know how many characters we've written in. And so the next time we do a slice, we'll start from there, and we can continue writing into it. If we have got data in there, we'll do an isValid check, and we can simplify that without regex here and just do is character or digit. And we basically finally end up here, hopefully, where we're going to use this memory extensions type here to lower invariant, which means copy this input string into this span area and lower it at the same time. So we can let the compiler do some optimizations, hopefully. So that's all we're essentially doing. In remove spaces, it's a fairly simple case of seeing if there's a space in there by using this index of on the span. And if there is, then we can take that actual index where that space is and just replace the character. So we can modify by using the indexer as well. So that's the code. It's all on GitHub if you want to kind of dive into it in more detail. But I'm going to jump back to slides and sort of have a look at the results here. So these are the results of my test. So in the original approach, just over 1,000 nanoseconds. And then we got down to 449 nanoseconds, so 2.5 times faster. Not a massive improvement, really. And depending on what our objectives are, that wouldn't be particularly great. But we were going really after allocations. We had a theory originally that might be a lot of allocations. And so we can see that the original code allocated, because it was using those things like string join and then string to lower, because strings are immutable, that means we're just creating new and new strings for each of those intermediate phases of building that final key. We have a fair few allocations, over 1,000 bytes here. In the new code, we have 192 bytes. And 192 bytes here is actually the length of the final string that we allocate at the end of the method. So we've achieved building that string with no overhead at all. And so that's quite a significant improvement for us. I slightly spoiled it by showing it a second ago, but on its own, this doesn't look super impressive. But we scale this up to what this service is actually doing. It's doing 18 million messages a day through this service. So that's 17 gig of daily allocations we've achieved just by modifying this one particular method flow in the code. And that's around 2,700 Gen 0 collections from the garbage collector that we've avoided having created and the need to do. So this at scale starts to sort of have compound interest, really, in terms of the investment that you're making. So moving on a bit, there's quite a few more features I want to touch on. ArrayPool of the first of those. It's really hard to work out what this does by the name. It's a pool of arrays. This is useful in scenarios where you regularly need a short-lived buffer, and you'll see this a lot if you're working with streams, for example. You need that buffer space to do some work, and then you're kind of getting rid of it when you've done something with it. What we can do with the array pool is we say, well, actually, we'll go to this thing that's going to have a set of arrays for us, and they're just going to live forever, essentially, inside our application, and the pool's just going to give us an existing one whenever we need it again. So that's quite powerful. It's found in the system buffers namespace. And the way you work with this is it's a generic type, so you sort of have an array pool of whatever you want. And typically what you'll call is its shared method, or its shared property, sorry, to get an instance that's kind of pre-configured with common pooling sizes that we might want to use. The reason it's a good idea to use this is they take care of sort of figuring out how to actually implement array pool itself. But also, this is shared with the runtime as well. So if we have an array pool of int, and the runtime's also using the same array pool of int, we've already got probably arrays in that pool that we can be sharing and reusing. So to get the item, we just call rent, and we give it a length. So we say, OK, I want 1,000 bytes, let's say. And it's going to give us back an array. The important and really critical point with this is you may get an array, and you probably will get an array that's actually bigger than what you've asked for, which sounds kind of weird. But it's logical if you think about how the pool is going to actually be functional. It needs to keep certain bucket sizes of arrays available so that it can give you a realistic reuse of those arrays. If you have every possible array size under the sun in the pool, you're realistically ever going to use that array once. And all we've done is just give a lot more long-life objects, and we've not really got any gain. So when you're working with the arrays from the pool, you kind of need to track how much data you've written into it so that when you're later iterating that array, for example, you only go to the length that you care about. When you're done with it, you return it. That's important. Otherwise, you've just created an object and cast it away. It would eventually get GC'd, but really all you've added is the overhead of an array pool with no actual benefit, so you're in a worse place if you don't return it. We can pass this clear array equals false or true through to this method. This is another important point. So before .NET Core 3.0, so 2.2 or earlier, when you returned an array to the pool, it was not cleared by default. This is a performance optimization that just saves a short amount of time clearing that memory. But it confused a few people, and it introduced a potential security risk if you were putting arrays back in with data that you didn't really want to be pulled back out again later. So now it clears by default, but you can turn that behavior off. You always need to remember that any array you're given from the pool may already contain data, which is why, again, you don't want to just iterate the entire array because you might be talking and getting data at the end of it that you didn't write into there in the first place. So it does somewhat complicate some parts of working with the array, but as we look in the example, it's not hugely complicated to do. So here I've got a short-lived buffer that I want to pass into another method, and here we have an allocation on the heap. So what I'm going to do is change that to, using the shared array pool, I'm going to rent 1,000 byte array. The chances are here I'll get 1024 bytes or maybe 2048 bytes, but it depends what's available in the buffer. It could go even bigger. But I've got my buffer, and then I can work with it. Now, as I say, we need to make sure that we put this back. So typically, they recommend using the try finally pattern here to make sure that whatever happens, we do return the array to the pool after we're done with it. And that's kind of ArrayPool. We'll see that in action in a moment. But I also want to introduce system I/O pipelines. This is kind of the brainchild of David Fowler and the ASP.NET team originally. So it was originally created to improve the performance of Kestrel. Kestrel does a lot of I/O. It's reading network requests off of a socket and then pushing them through the Kestrel web server into MVC or Razor Pages and into the side of ASP.NET. And this is quite a heavy operation because there were various handoffs between different streams through those different layers of the application. So they were looking for a way to optimize that code, and they found that they can actually improve working with streams by about 2x. Now, you could technically write that code yourself. That's all they've done. But they've wrapped it inside this type because it's actually really, really hard to do. So it's really just removing the boilerplate of trying to optimize streams yourself through this type. The important thing about the way that pipelines work is, unlike a traditional sort of stream-based approach, you're working with the buffers yourself and you're managing those. The pipe is going to do that all for you. So it's going to hand you some memory that you're going to work with, and you're going to just read out of it. And you don't need to worry about the buffers. And it's also going to use the array pool internally to do that, so it avoids heap allocations for those buffers as well. Two ends to a pipe. It seems quite logical. We have a writer and a reader. So what does this look like? Well, we have a pipe. So we're first going to start working with the pipe writer. So when we get the pipe writer, what we can do is we can say get memory. This gives us a memory of T. Memory of byte in this example. Why memory? Well, we're inside an async method typically when we're working with this. We're going to be doing some I/O within the same method, so there's likelihood of async calls in there. So we get a memory of byte. We would do some work with that data that we've been given to put some data into it, maybe how I built up the character array before for my object key, for example. And when we're done, we just advance by the amount of bytes we've written, and then when we're ready, we can flush it as well. Flushing it is the operation that signals to the reading end you've got some data that you might want to look at now. So on the reading end, we have a pipe reader. We can await the read async method. So it's a non-blocking operation by default, which is really quite powerful. It's not going to do anything until there's something in that pipe that we haven't already seen. We get back a read result. On the read result is a buffer. And that buffer is, interestingly, of type read-only sequence. Why read-only sequence and not memory? Well, the reason is the pipe in advance doesn't generally know how much data you're going to give it. If you're streaming data off of a network socket, you might get a small amount of data or you may get lots and lots of data. So the pipe has to be able to create buffers for you as it gets more and more data as those buffers are filling up. And what it's going to do, essentially, is create lots of memory of T's off of the array pool internally. And then when it returns it to you, it gives you this structure of a read-only sequence that just represents essentially a linked list of those buffers so that you can then work through them as if it was one logical piece of memory. So this is how you're going to be sort of operating on the data that you get back from the pipe on the other end. So this, again, is easier to see in practice. So what I'm going to do in this example, the scenario here is tab-separated file parsing, which is super exciting. We had a scenario where we parse a tab-separated file that was stored on AWS. We first decompress it, which is kind of unimportant for this example. But then what we're doing is parsing that data and getting basically just 3 parts of it, 3 particular properties out of each row, and storing them into Elasticsearch. So let's look at the code for this. And again, I'll do the sort of before and after code, and then we'll look at the actual improvements. So this is the before code. Again, I'll just sort of quickly go over it. So essentially, we read, in this case, from a file, just because I didn't want to be using S3 in my example, but we get back a stream from S3 as well. We would decompress it. And eventually, what the original author of this code was doing was decompressing the entire stream to an array in order to create a long string that represents all of the data in that file. And the reason they were doing this is they're using this library called TinyCSV Parser, which at least at the time I was told only accepted working with strings. These files are about 10,000 rows each, So if you start to think how much memory that might be if we create a byte array that represents the file, and then we could create a string for it, this was setting off some warning flags. And we did actually have some memory leak issues with this service that led me to look at it initially. So what I've done instead is, what they were using was this tiny CSV parser, which has this quite nice sort of fluent syntax for kind of saying, I want to read this out of it and map it to these properties. So the reason they were using the library was readability and convenience, but I had some concerns. So the new code, again, I will just show you for comparison. This is longer, again, but hopefully something we can follow. So we start with the decompression stream as before. So we're going to use the pipe here. With a stream, we have to use a stream at the early stages because there isn't really a pipe that can decompress at this point in time, but that may well come with the framework. But once we have a stream, we can just create a pipe reader over that stream and start working with the other end of the pipe, basically. So the framework will handle writing into it. We do the read async, as we saw in the example. We get the buffer, and eventually what we're going to do is call into parsed lines, passing in the buffer. What this is doing is, so we've got a sequence reader, which is a type that allows us to work with sequence in a very convenient way, because that read-only sequence type is a bit of a pain to actually parse your way through, but the sequence reader makes it quite straightforward. It gives us methods like try read to any, where I can say, look for, in this case, the bytes that represent a new line character. If I've got a complete line, I know I can parse the actual elements out of it. If I don't have a line, we'll break here and we'll wait until more data comes from the pipe. When we do have at least one complete line, we'll try and parse it. And inside parse line, we're kind of dropping now down to a span-based approach. And all I'm looking for in this case is within that span, find me the index of the tab byte and count your position through by using that tab character as the way of identifying where you are. So when you're at tab count 1, I know I want to read that string. So all we then do is slice from, in this case, the start position to where that tab is. And now we've got some data that we can immediately cast to a string that we're actually going to index into Elasticsearch. And we just do that for the items we want. We break out early. We only do the 11 tabs, because after that, we don't care about the rest of the line. So we've done some optimization by not even parsing data that we don't care about. In terms of performance gains for this, let's look at the results. So I did this test over 75 files, each with about 10,000 rows, because that was kind of representative of a load I was seeing quite often in the service. So in the original, we're about 8.5 seconds, and we're under a second in the optimized code. That's quite good. It's not like super exciting. This is a processing service. We could probably live with 8.5 seconds. But the allocations was a really telling story. 7 gigs of allocations reading through those files in the original flow because of that byte array that we're creating, and then that string copy of memory. There's a lot of copying going on. There's a lot of allocations going on, short-lived allocations. We're down to 242 megs in the new flow, which is quite a significant drop, 30 times roughly less. What was really interesting was 203 meg of that are these strings that I'm outputting into the data that I'm going to push into Elasticsearch. So that means we're sort of less than 40 meg of overhead for this piece of work to happen now, which is quite significant. And actually, I can optimize a lot more of that away because Elasticsearch accepts bytes. So I could actually avoid those string allocations entirely, potentially, with my code in the future. So quite a lot of advantages that we were able to get with pipelines, span, in that example. So finally, I want to touch on the JSON APIs that came in .NET Core 3.0. Out of interest, who heard of like system.text.json when it arrived? Pretty good number. You read the blog posts. So this came in the box. Microsoft announced it. It did cause a little bit of heat on Twitter when they first said what they were doing, because everyone started sort of stamping on Microsoft saying, OK, you're going after the open source community yet again. We have Newtonsoft JSON. We like that. Why are you building your own thing? Now, fortunately, to kind of help ease that, James Newton King, who wrote JSON, Newtonsoft JSON, came up and wrote a blog post and explained why he thinks it's a good idea. Now, to be fair, Microsoft have employed him, so he's paid to agree with them. But you know, hopefully, his points are fair, and he probably is representing his own viewpoint. And the reasons for this were twofold. So one of the issues was ASP.NET Core relies on JSON parsing quite often in order to do model binding with data comes in as JSON and to serialize data out in web APIs. This means that for that to work, they have to pin the ASP.NET Core version to a particular version of Newtonsoft JSON they know works, which means that if you want to use a different version in an ASP.NET Core app, you probably can't, because it won't actually get brought in by NuGet. And that was a bit of a pain for certain people that wanted the latest JSON features, but were tied back to whatever ASP.NET Core had at the time it was released. The other problem is performance, and there are ways to optimize, obviously with things like span of t, but to retrofit that into Newtonsoft JSON, which is installed in so many millions of code bases, which would introduce some kind of breakages to the API surface, would have been a bit of a nightmare for anyone that decided to take the next release. So rather than break everyone in the world, they decided it would probably make sense to just build something in the box, because this is done so often, that ASP.NET Core can rely on, and optionally you can use too, or you can continue to use Newtonsoft JSON. There's 3 layers to the way they've structured this. So at the bottom level, the lowest level that gives us the most performance, we have a UTF-8 JSON reader and a UTF-8 JSON writer. This is where it gets really gnarly, and we'll see some code for this in a moment. But this allows you to get the most sort of bang for your buck. If you're really looking for performance, then you can work at this level. If you're actually reading data, a slightly more sort of less verbose way and a slightly efficient way to do it is with this JSON document type that they've bought. This is essentially a read-only view that in most cases might not actually even allocate any heap memory when it's working. It gives you essentially a document object model of JSON that you can parse your way through if you want to. And then at the very top level, we have a regular serializer and deserializer that are optimized. They are quicker than Newtonsoft JSON, but they're sort of less performant than working at the low-level code yourself, because they have to be a bit more generic and a bit more general to the JSON structure they get in. Those serializers are quite sort of feature-limited at this case. They were released with just what was enough for ASP.NET Core serialization primarily. That is being moved on in new versions of .NET Core, but just be aware that A, they're limited in features, and B, they're quite strict about the JSON structure. Newtonsoft JSON is quite good at working out what the JSON probably means, even if it's not entirely valid JSON. System.text.json will just generally throw an exception if it encounters invalid JSON. So this one is easier to see in practice again. So here I'm going to do an example where I'm going to index something into Elasticsearch. It doesn't matter if you don't know what Elasticsearch is, but it has an operation that's essentially a REST endpoint I can call to parse it some data to store in the index. What I need to do is when I get the response back, I need to deserialize that response in order to identify, did that operation complete successfully overall? And if it didn't complete overall successfully, which of the actual things I indexed failed? Because what we want to know is which ones we have to retry. And so this is actually quite a sort of hard problem to do in a very efficient way with regular JSON. So let's look at the original code. Now, the good thing about this code is I can, even at this ridiculous font size, fit the entire method on the screen. So that's good. And we're basically just taking the JSON text reader over the stream of data, deserializing it to our type. Now, inside that type, basically the data that you get back from the Elasticsearch API is how long it took, true or false, were there any errors or not, and then the collection of all the items, which is the metadata about everything within the request that we made. What we can say is if there are no errors at that top-level property, then great, return that there's no errors, so success true in this case, and an empty array of items that failed because there's nothing. If there are errors, then we have to work our way through it to find the ones that had a failure code, and then we've got the IDs for those that failed. Fantastic. So we'll go to the new approach. You can tell by the scroll bar. It's a bit bigger. And again, you really have to make a judgment call on whether this is worthwhile in your scenarios. Again, some horrible stuff at the top we can skip over. So here we're using the ArrayPool. Fantastic. So in this case, rather than using pipelines, I'm going to use streams just natively. So I'm going to create the buffer for that stream, but I'm going to use the ArrayPool. So this gives us the flexibility to at least not heap allocate this temporary buffer. A lot of code here, so I'll skip over some of it. But ultimately, what I'm going to do is I'm going to read from the stream into my buffer, and then I'm going to try and parse the errors. And I pass a lot of stuff in by reference here because I'm going to track my state as I come into this method, because I might not have the entire JSON blob in one go. I possibly won't. So inside parse errors, we're going to use this UTF-8 JSON reader. This also takes this isFinal block Boolean and some state. So this is a reentrant type. It accepts the possibility you're working with streams or data that's coming in chunks. So it allows you just to kind of keep calling it with the last state that you had, and it can keep parsing through further and further into the JSON. And ultimately what we call is JSON.read. And inside here, once we've done that, we basically get the token that we're at. And we're low level now. We're looking at the opening curly brace of an object, or we're looking at the start of an array. But we have these tokens that we can work through. And all this horrible switch code does is try and work out, with the known structure that I know I'm getting, where is the errors property and what's its value, true or false on that one, and potentially, if I need to, the items. The interesting thing I can do here is, if I found the errors property here, and then on my next loop through, if I find false as the value of that property, then I'm going to break out of here, and essentially, if I come back up here, I short-circuit the whole process and say, well, if there's no errors found, or I found the errors property and it has no errors, stop. If that's no errors in that document, I don't need to parse through the rest of the JSON at all. That's within the first like 20 bytes of the JSON. So I can optimize this code to avoid parsing anything I don't care about. Only in the sort of failure case would it then have to go through and identify and find all of those relevant IDs for the messages that failed. Again, you can kind of have a look at that code at your own leisure if you're bored on a Sunday evening. But otherwise, I'll jump through to the results, which are a little more fun. So in the failure response scenario, and I'm totally frustrated with the numbers because I'm sure there's more performance. And this is the one risk you run with performance. Every time you see an allocation, you'll be like, ah. So even here, although we've gone down from 114K to 16K in the failure scenario, that 16K feels like failure. But this is a pretty good gain. But the failure response is really unlikely in our case. We're not expecting things to fail on the indexing process. So the success response is more interesting. I'll skip over those. So the success response here in the optimized flow is so much quicker because we read the first 20 bytes, we see if there's no errors, and we just dump doing any more work. And we only allocate, frustratingly, 80 bytes. That really should be 0, and I need to spend some time with this code to figure out where 80 bytes is coming from. But it's good enough as a prototype, and we've proved that in the sort of 99% case, we are saving a fair amount of allocations on what is going to be a fairly heavy and common operation in this particular scenario. So we're sort of wrapping up now. We're getting towards the end. And the important thing you might be thinking is, great, I want to do some of this. How do I get work to let me to do it? One, you can be sneaky and just do it. And kind of that's what I've done here. All of these prototypes are little lunchtime projects that I've done here and there where I've seen things that might be interesting. To take this forward, what I suggest is you look for one of those kind of things like I did where I saw heavy allocations. In my case, we had one service that was actually falling over because of memory allocation, so that was a clue we should probably do something. But even then, just looking at that code casually, you could see that array allocation, the string allocation was heavy heap allocation. So look for something like that where you can kind of say, yeah, that's really bad. Then use this scientific method of actually measuring first, optimizing a small piece of code, measure again to give you these numbers that actually let you quantify what you've achieved. Do not go to the product owner and go, I've shaved 1,000 bytes off of this particular method, and it's now only 400 nanoseconds, because they won't give a damn or they won't understand really what you're babbling on about. So turn this into a monetary value. Try and establish for them what the value of this is and give them some kind of cost to benefit ratio of you spending time doing this in work time or real time to actually move this forward. So this is one example we had. So we have a service that's an input processor. This is one of the things that's doing kind of 18 million messages a day. So fairly common high volume workloads. And so what I did is all of these individual prototypes, plus a few I haven't had time to show you, were attempts at finding various parts of that flow that I could potentially optimize. After some sort of like maybe slightly positively biased estimations, I've said that I think I can reduce 50% of the allocations inside this little microservice, and I can probably double its throughput based on the execution time changes that I'm seeing for the various phases. So then what I've done is gone and looked at how much scaling this service is having to do inside our container cluster to figure out, actually, I can probably get rid of enough scaling that means I save one VM in our cluster on a sort of daily basis, which is, in our situation, about $1,700 a year for that one service change. Now, that might not be enough to justify a developer spending their time on it, but some of those processes, particularly in microservices, if you're doing a lot of data manipulation, you'll be doing the same thing time and time again in lots of services. And if you can just kind of stamp and replace similar parsing logic for those particular requirements, we can ramp this up quite quickly at scale across the many hundreds of services we might be talking about. So you can start to show this value, and you can then sort of see if you can get the business to actually buy into this idea of actually optimizing the code. Again, where it's contextually worth doing. If there's a good cost saving and the code doesn't change much, this might be good for you. So in summary, because this has like been a lot of stuff for an afternoon, I can't even remember what I said at the start. Everything you've seen is really, importantly, mostly for advanced situations. So this isn't stuff you go back to Office on Monday and go, ooh, I'm changing everything, spam's going everywhere. It's really tempting, and when you start, it's hard to stop. But use some caution around where you're applying it. Measure everything, don't assume. Assume, in this case, can be really dangerous around making changes that are actually degrading performance or having a knock-on effect elsewhere that you just couldn't actually even foresee. Be scientific in that. So benchmark.net is a fantastic, quite easy tool to get going with initially that gives you these kind of accurate numbers that you can work against. Focus on the hot pass. Don't spend all your time optimizing something that's called once in a blue moon. It might be fantastic that you get 0 allocations, but is that actually going to change your life in terms of that service's overall code? So don't copy memory where you can. Slice it. Work with the span APIs when you're doing parsing of strings or byte data. Use those ArrayPools. That's quite a quick and easy change you can apply with fairly insignificant code changes, actually, and it's still fairly readable code when you finish it. It's not quite as bad as some of those demos I showed you overall. Pipelines is great if you've got a lot of I/O, so can keep that in mind there. And the new APIs for JSON, if you are doing that JSON parsing, as I've shown, you can make some really efficient sort of API calls and parsing of the responses you're getting with that kind of API. One book I would recommend, Pro.NET Memory Management. Conrad's here at the conference. He spoke yesterday on 0GC. Fantastic book. It's about this thick, and if you carry it around, not only will you get stronger, but you're protected at night if someone comes and attacks you. Swing your bag, you kill them. It's really worth having, and this is where I've learned a lot of what I've seen in here about how .NET works around memory and how you optimize and use span. I'll leave the link up with the slide there. Again, if you want to get in touch afterwards, please do follow me. I'll tweet about this, ASP.NET Core and Gin, or you can check my blog, which is limited to actual technical stuff. Otherwise, thank you very much. Time's up. Thank you.